The climb section of aircraft performance deals with the analysis of that stage of flight from takeoff to the en route or cruising altitude. There are primarily two ways in which we can judge the performance of an aircraft in the climb. Firstly, by considering the angle or gradient at which the aircraft climbs, and secondly, by looking at the rate at which it climbs. We'll examine the angle or gradient of climb first. Shown here is an aircraft in unaccelerated level flight. Notice that the forward acting force, thrust, balances the rearward acting force, drag. Therefore, the aircraft maintains a steady speed. However, when the aircraft attempts to climb, as shown here, a component of the aeroplane's weight acts backwards along the longitudinal axis in the direction of drag. This component is known as weight apparent drag. It can be calculated by multiplying the weight by the sine of the angle of the climb, gamma. You'll now notice that the magnitude of the rearward acting force is now more than that of the forward acting force. If the situation were left unchecked, the aircraft would decelerate. To maintain a steady speed along the flight path, an additional amount of thrust is therefore needed to balance the magnitude of the weight apparent drag. This is known as excess thrust. You'll notice now that the forward acting force in green matches the rearward acting forces in red, and therefore the aeroplane is able to maintain a steady speed along its new flight path. To maintain a steady climb with no loss of speed, thrust must balance not only the aerodynamic drag, but also the weight apparent drag. The larger the excess thrust available, the greater the weight apparent drag that can be balanced. In other words, the more excess thrust available, the steeper the angle at which the aeroplane is able to climb. If the aircraft only has a small amount of excess thrust available, then notice now that there is too much weight apparent drag, and that the angle will need to be reduced so that the excess thrust available balances the weight apparent drag. The excess thrust can be calculated by taking the total amount of thrust available and subtracting from it the amount that balances the aerodynamic drag. The thrust remaining is the excess thrust available. From what we've just seen, for any given weight, the angle or gradient of climb depends on the amount of excess thrust available. Here is the formula used to calculate the gradient of climb. Remember that when we subtracted total aerodynamic drag from the total thrust available, we got the excess thrust available. For any given weight of aeroplane, the greater the excess thrust available, the steeper the climb angle. The smaller the excess thrust available, the more shallow the climb angle. So, in order to maximize the aeroplane's climb angle, we need to maximize the excess thrust available. In order to discover how the aeroplane concerned can maximize its excess thrust, and therefore maximize its climb angle, it will be necessary for us to see the thrust and drag data. Let's first deal with the data for a jet aeroplane. Shown here is a typical graph of total thrust available and total drag for a jet-powered aeroplane. Excess thrust available is the amount of thrust that exceeds drag. Here, excess thrust available is represented on the graph as the area between the thrust and drag lines. You'll recall that to maximize the gradient of climb, excess thrust available must be at a maximum. This is the case where the distance between the thrust and the drag lines is the greatest, as shown here. Notice that maximum excess thrust available occurs at this speed. At any other speed, the excess thrust available is less, and therefore the achievable climb angle will be less than the maximum. The speed at which the aeroplane generates the greatest amount of excess thrust, and is therefore also capable of its greatest angle of climb, is called Vx. Vx is defined as the speed for the best angle of climb. However, in order to appreciate what value this speed represents, it's necessary to mention some other speeds at this point. There are three such reference speeds which are used in aeroplane performance. The first is the velocity for minimum drag, or VMD. VMD speed is found at the bottom of the drag curve, as shown here. The second reference speed is the velocity for minimum power required, or VMP. VMP is about 0.76 of VMD, as shown here. The last reference speed is found at the tangent point to the drag curve, as shown here. This reference speed value is 1.32 times the velocity of the minimum drag velocity, and thus it's referred to as 1.32 VMD. Having identified the reference speeds, the most useful point to remember is that for a jet aeroplane, the speed for the best angle of climb, Vx, occurs at VMD. Flying at VMP, or 1.32 VMD, would not generate the same value of excess thrust, and therefore would not generate as steep an angle of climb as would be achievable if the aeroplane were flying at VMD. Having discussed the concept of maximum excess thrust and the speed Vx for a jet, let's now examine these concepts as they apply to a propeller aeroplane. Shown here is a typical graph of total thrust available and total drag for a propeller-driven aeroplane. We know that excess thrust is the amount of thrust able to be developed by the engine in excess of drag, and it's represented on the graph as the area between the thrust and drag lines. You'll recall that to maximize the angle of climb, excess thrust available must be at a maximum. Excess thrust available occurs where the distance between the thrust curve and the drag curve is the greatest, as shown here. Notice that maximum excess thrust occurs at this speed. At any other speed, the excess thrust available is less, and therefore the maximum achievable climb angle is shallower. Therefore, Vx for a propeller aeroplane occurs not at VMD like the jet aeroplane, but instead at VMP. Let's now examine what factors alter the excess thrust available and therefore the angle of climb. The first of these factors to consider is the effect of weight. Shown here is an aircraft in a steady climb. If we now increase the weight of the aircraft, notice that the aeroplane will have more weight apparent drag. The forward and rearward forces are not balanced, and the aircraft will decelerate. In order to maintain speed in the climb angle will need to be reduced so that the weight apparent drag is less. Now you can see that the forces are once again balanced, but the climb angle is shallower. This effect can also be observed in the formula we use to calculate the gradient of climb. If the weight increases, then the excess thrust is divided by a larger number, and so the gradient of climb will be less steep. Weight has another effect on the angle of climb, though. An increase in weight will require an increase in lift. If lift is increased, then lift-induced drag will increase, which in turn will increase total drag. This increase in drag will reduce the excess thrust available. Notice now the present value of excess thrust is not able to balance all of the weight apparent drag. Therefore, the aeroplane climb angle must be decreased to reduce the weight apparent drag to a value that can be balanced by the present value of excess thrust. However, the effect of weight on drag is a bit more complicated. Shown here is a graph representing induced drag, parasite drag, and the total drag. You may recall that we stated that if we increase the aeroplane weight, it will require more lift. Creating more lift will increase induced drag, and as a result, the induced drag curve will move upwards. Notice, though, that the total drag curve has moved as well. In fact, it's moved slightly upwards and towards the right. It's important to remember the fact that increasing weight moves the total drag curve up and to the right. Returning to the excess thrust graphs for the propeller and jet aeroplane, it's now possible to see the effect of the movement of the total drag curve. Increasing the airplane weight moves both total drag curves up and to the right. Notice, as mentioned earlier, that there is a decrease in the excess thrust available, and therefore a decrease in the maximum achievable climb angle. However, it's important to realize that the speed for maximum excess thrust available is higher. We've seen that for both jet and propeller aeroplanes, as weight increases, the speed Vx will increase. This means that although your climb angle will decrease with a higher weight, in order to get the best possible climb angle from this deteriorated performance situation, you'll have to fly at a higher speed.